Welcome, everybody, to the AIAA Space Resources webinar series hosted by the Education and Outreach Subcommittee of the AIAA Space Resources Technical Committee. My name is Jared Longfox. I'm one of the co-hosts and organizers of this webinar series. Today, we're fortunate enough to have Jonathan Slavic from Astrobotic Technologies presenting applied propulsion, rocket technology, enabling space resources to us. I'll hand it over to John in just a sec, but as always, if you guys have questions, comments, or concerns, please punch them in the Q&A and we will get to them after John is done presenting. And yes, I do see a question in the webinars already, or in the Q&A already. So I will absolutely be making the slides available. And if you can't get them on AIAA Engage after, please let me know and I can send them to you directly. Thank you, Andrea. I will be sure to send them to you. So sorry about that. And without further ado, John, take it away. And thank you for presenting.
All right. Hi, everybody. My name's John Slavic, and as Jared introduced, I'm at Astrobotic Technology, and I am part of our research and development group working out of the Mojave, California office, working on a lot of propulsion systems for rockets as well as ISRU technology. So today I'm going to be presenting our applied propulsion effort, sort of how rockets and propulsion generally fits into the world of space resources and sort of understanding how we came to put those two together and what advantages they bring working together. So without that, let's jump into an overview of what we're going to be looking at today. So we'll start off with Astrobotic at a glance for anyone who's not familiar with who Astrobotic is and what we do, and then we'll get kind of into the start of the applied propulsion group, what sort of led me and the team to figure out that this was maybe something we should be working on and a theme that we should be working towards. We'll talk sort of about our plume surface interaction testing that led us there, and then we'll follow up with sort of our conclusions from plume surface interaction testing and how that led to this applied propulsion approach, and then we'll talk about some solutions, some propellant-based solutions to a lot of the vexing ISRU and space resource challenges that we face going forward, and sort of comparing those to the state of the art and sort of where they're complementary and where they're different. And we'll finish up with a short discussion about how this all plays into the lunar economy. So yeah, without that, let's start with Astrobotic at a glance. So many of you, if you've heard of Astrobotic, have probably heard of us as one of the NASA Commercial Lunar Payload Services providers. So one of the CLPS companies going to the moon. So we provide landers like the Peregrine and Griffin landers, but also we in-house develop a number of sensor suites and capabilities for precision landing to actually get us to the surface. And then we also develop a number of rovers and rover technologies for mobility on the surface. And that really leads us into our surface power capabilities as well, where we're trying to not only just be able to land on the surface, but provide power and infrastructure once we're there. And as a big part of that, then on the far left there, we've got our rocket technology, our vertical takeoff, vertical test, hover test beds that we operate out in Mojave, California, where me and my team are based out of. So kind of some major projects then, just sort of more specific than that broad overview. We had the Peregrine Mission 1, which was the first CLPS launch towards the moon. Obviously, that was more of a stayed as an orbital mission, unfortunately, due to an anomaly we had there. But we're following up with Griffin Mission 1, which is our much larger lander that was initially slated to fly Viper to the moon before that got called off, but is still flying at the end of the year with another rover payload from Astrolab on there. So we're very excited for that. We've also got our Cube rover missions going forward and some other mobility missions, as well as our Lunagrid power systems and our Zodiac and Zogdor vehicles that are both operational. Zodiac's operational and Zogdor's under development as vertical takeoff, vertical landing testing beds. But getting a little bit more into the propulsion side of things, I work with a group, our Mojave, California group, as I said, that we call our propulsion and testing office. That was formerly Masts and Space Systems. So I came over I was at Maston and came over as part of an acquisition where Maston was purchased by Astrobotic. And that Maston team brings 19 years, actually, I think it might be 20 now, but yeah, a number of years of vertical takeoff, vertical landing experience, right? So we've flown all of these different vehicles here and have a lot of experience with both rocket technology, plume interactions, and all the work associated with that. And in developing these rockets, we've developed a lot of sort of adjacent technologies as well. So a lot of, advanced manufacturing for rocket engines, advanced types of rocket engines, focused a lot on landing pads, heat systems. There's a little preview of a lot of the things we're going to talk about later in the presentation as we start talking about what really is applied propulsion. And so to that end, let's see how we got there. How did we start using the term at Astrobotic applied propulsion? Um, not to just read off of the slides, but I particularly like this one of it's using rockets for things that are not propulsion. So when you have a hammer, everything looks like a nail. We've got a lot of rockets hanging out in Mojave, and not just the ones that we put on our vehicles, right? We have a lot of development rockets as well, things that we would use to say, well, I want to test out this particular component or injector geometry or something else, where we're going to make a test stand only rocket that we're going to fire and we're going to validate some components to infuse them into another vehicle or another larger rocket engine. So we had all these sort of extra engines, and we were thinking, what can we do with these? And we realized, we're out in the desert. We could do some really interesting plume surface interaction evaluations where we're shooting rockets at dirt to see what happens. And so that oversimplifies it a little bit, but we'll get into to what those studies really mean. So with that, we're going to switch from the fun stylized slides to the more academic white background slides. So what is plume surface interaction? Um, that is the gas that is exiting a rocket nozzle interacting with the things around it. Some people may be familiar with plume studies for in-space applications where we're really looking at how do those plume gases adhere or freeze out to different surfaces, or how do they radiatively heat things? We look at that plume evaluation pretty often. But for plume surface interaction, it's mainly what kind of dust and dirt are we kicking up as we're landing, right? So we saw this in the Apollo missions. We saw this with the recent Eclipse landings, and we know that a lot of things get kicked up, but really understanding it is really challenging because we can't just go back all the time and look at it. As much as we'd love more lunar landings, that's not always an option. So really, the main way we end up looking at this is through computational models, where we're trying to simulate what's happening in a vacuum in a low gravity environment to say, okay, is this landing going to be okay? And that really, we use terrestrial testing data, the stuff that we're developing, to anchor those models, right? Where we can use them to look at mainly crater formation and ejecta velocity, and we'll talk more about both of those topics here in just a second. But so we had all these rockets laying around. So what are we going to do with them? Well, we started by going to the SBIR program, and we were able to go phase 1 through 3, which was pretty exciting in that just doing a lot of testing, firing rockets at the dirt to figure out really, can we measure what's going on? Can we characterize what's going on? Can we get useful data out of doing that we can use to anchor these computational models? So we ended up taking the small engine that we had been using for injector testing, and we mounted it over a big bin of regolith simulant, and we fired into it. So that was kind of phase 1. And then in phase 2, we started doing split view testing, where we were actually able to cut the plume in half and view the evolution of the crater as it was forming. And then we're able to try and track some of the ejecta in a more sort of coarse manner, where we're looking at individual frames of a high-speed camera to say, where are they going? What direction are they going? How fast are they going? And then actually at Purdue in our phase 3, we were able to try and do some vacuum testing, where we put the regolith bed and the rocket engine in a dirty vacuum chamber and fired into it to try and produce these same effects in vacuum, which is challenging. On the far bottom left, you can see some work that we did with UCF on drop towers and vacuum to try and simulate some of this with cold gas. But yeah, it really kind of showed us what is possible and sort of where there are some areas where we want to be able to learn more about the capabilities that we want to develop with PSI testing. So pictures and me talking about it are fun and all, but let's watch a video. So this is we're looking at the side of a regolith bed. It's a little scrappy pulled together, but when we're out in the middle of the desert, it's a little tough to have it more buttoned up than this. But we're gonna fire the rocket into the top, and this is slowed down. So the rocket's only firing for 2 seconds, but we'll see the evolution of the crater formation there. So you can see this is from our phase two effort where we're doing our split view testing, where you can see the rocket. This is about a 100-pound rocket firing straight down into the regolith, and we can see in real time this crater forming. And really, what's valuable about this is being able to look at doing something similar with a computational model and seeing if the evolution of the crater matches between the two. So we know when we're doing our model, is it actually relevant? So since we were starting to do shooting these rockets at different things, we actually had another program that was pretty fun that we called it was for the Air Force Research Lab and called it Tech Sprint, and it was a sprint because they had a bunch of different materials that they wanted to shoot rockets at and see what happened. So various landing pads and unimproved surfaces and things like that we wanted to look at what does that do? So I really like including this because it has a really fun video associated with it. You'll see some changes on the stand here. Here we're looking kind of down at the engine, and we modified the test stand. We actually, instead of having it statically firing down, we put it on an old car lift, and we're able to go up and then drop it back down to simulate landing on a surface so that the engine actually moves relative to the landing surface. So let's see this one fire. Again, this is slowed down. The engine's only firing for 2 seconds. Um, but yeah, so we're seeing it move quite a bit slower, but you can sort of see all of the ejecta effects and the engine getting pretty dirty. So it's pretty unique that we have an engine that we can repeatedly put into this environment, and we haven't had it blow up very often. So it's pretty nice that it's been robust to that. But as you saw from the previous video and from this one, we've got high-speed footage that we can kind of see qualitatively what's going on, but we really wanted to bring this into a quantitative world to understand these plume surface interactions. So we started a program called Psychic, as we were calling. We're working with Texas A&M on this one and this is just a combined hot fire imaging camera. So we were able to combine footage from our high-speed cameras and also viewing it with thermal and then a neuromorphic camera, or actually two of those cameras, sometimes called event cameras. And really what's nice about those is they see what's moving and not anything else, kind of like T-Rex in Jurassic Park. They can only see what's moving. But what's valuable about that is they can go really, really fast. Frame rate is the wrong term because of how they work. But if you look at a high-speed camera, you've got 1 millisecond per frame. And with the neuromorphic cameras, we're down to 5 microseconds per frame. So we can really see these particles move very, very slowly. And we can track them. So in the top there, you can see we were doing some work on particle identification and tracking where we can get instantaneous velocity. And then we were able to do that in stereo to build a three-dimensional view of where all these particles are. So this is still very much in the development phase. I wish I had a cool 3D model recreation of a plume event to show you, but that's something we're working towards. But as like some of our early proof of concepts, on the left, you can see a high-speed video, and on the right is the neuromorphic camera. And this is, they're matched to 1,000 frames per second. And this is just cold gas. This isn't a rocket firing. This is just a spritz of nitrogen. But as you can see, it isolates, hopefully it's not too choppy on the view for everyone, but it isolates each of those individual particles. And as you saw in the last slide, we can track them individually in an automated sense. So rather than trying to look at, okay, well, this moved 3 inches during, between these two frames. So here's our estimate for its direction and velocity. We're able to get much finer granularity about the velocity and trajectory of these ejecta particles. So in the split view testing, we're able to see the crater formation. And then with the psychic tests, we're able to see the ejecta and really understand what's going on with them in a terrestrial testing sense. And then the next thing we worked on sort of, and this is, we're going to walk through all of these PSI efforts and sort of come to a conclusion about what that means and then how that plays into space resources. But we were actually able to develop, we're working on developing a test stand where we can not only go into vacuum, but we can gravity offload and do hot fires during gravity offload, which has been a real big challenge for us. So really what we discovered and working with Phil Metzger on a bunch of this stuff is that we don't want to just simulate lunar gravity and Earth gravity, right? That's just 2 points. And if you're trying to come up with a quantitative description of how these craters form, that you want to have more understanding of the interaction between, let's say, like the cohesive forces between dust particles and gravity. And like, if you only have 2 points, the best you can do is correlate those linearly. Versus we're developing this system to be able to vary the gravitational constant, so dropping at different speeds as we're doing crater formation to understand, to be able to curve fit what those computational models look like and get a much higher resolution and better confidence in those models. So here's sort of a view of our phase one effort that we're just putting together with cold gas to prove out that the stand could work in this configuration. Um, where we've got, instead of dropping the engine onto the test bed, the test bed's falling with the engine. So here's how we did it with cold gas. So the whole thing's firing and doing crater formation as it's dropping down. So it's not very far, but this is our phase one proof of concept. On the left, on this one, you can see crater formation, reduced gravity. On the right, you can see it statically. So this one's a little longer. But what we're really interested here is just proving that we could get a differentiation, which is pretty exciting. The crater formation is a little hard to see here. It's a little dark, but you can see on the left, it's a little bigger. On the right, it's going a little slower in the static case. So we're able to show that offloading actually does get us somewhere. And we can see the different shapes of crater that are formed with that change in the G parameter. So all of that leads us into PSI modeling, right? We're doing all these tests to anchor computational models. And got any analysts in the audience, please cover your ears. But what I like to say is that all models are wrong and some models are useful, right? You're never going to completely simulate the effects of the real world. What you're trying to do is get a useful model of some aspects of reality. And what we're trying to do with these tests is we're trying to make those useful aspects as accurate as they can be, right? So we're working both with UCF and Texas A&M on development of different models, both to look at how those flow fields affect crater formation and ejecta trajectories, and especially starting to incorporate particle-particle interactions into these models, because those are very computationally heavy, but we're also showing them to give us better results in terms of ejecta angles that are more representative of reality. So that was sort of the work that we were doing when we said, hey, we've got all these rockets. Let's shoot them in some dirt. Let's see what happens. It was really to come up with the anchoring data for these computational models. But what do these models and all of these tests tell us? What are the conclusions here? Well, it's mainly rockets dig holes, which is a problem. You'll see this image in the upper right a couple of times because I think it's really illustrative of the issue, where at a certain point, like with the Apollo landers, we get scouring, we get very shallow craters. But as you increase the mass of the lander, not necessarily getting the engine closer or further away, that is a factor, but it's less of a driving factor than the mass of the vehicle. As you get to certain masses that you have to support with that plume gas, you start doing what's called deep cratering. That was what we were seeing with the split view testing and all these images where you can see this really pretty view of the crater forming. You don't want that. That is bad. You don't want a deep crater. One, because you could fall into it, right? That crater is pretty big relative to the lander. And two, I'm sure a lot of people have seen the little swirly picture over on the in the center here. That's some work that Dr. Metzger did to show that ejecta from an HLS class size lander could go into orbit around the moon and more specifically cross the gateway orbit. So it could be very dangerous, right? Where we could be not only damaging surface infrastructure like we saw in Surveyor 3 and Apollo 12, but we could be damaging orbital infrastructure, which could be very problematic for the nascent cislunar economy, both for space resources on the surface and things in orbit. So we've been lucky up till now is the takeaway, and we need to do something about it. So that that then begs the question, what do we do about it? The obvious solution, which I am, not original to me, is we need landing pads, right? We need to be able to land without kicking up all this dust. Fair enough. But a lot of the solutions that we're looking at for landing pads, very reasonably include space resources, right? I like including this image from Ethos with their paving system there. I think that's very cool. Microwave sintering, laser sintering, basaltic casting. There's a lot of options where we can use just the regolith to create the surface infrastructure we need for landing pads. But there is sort of a chicken and the egg problem here, right? Where I alluded to earlier, this PSI issue scales with mass. And to be able to do this kind of surface development, we need a lot of mass, whether it's power infrastructure, whether it's vehicles, whether it's site preparation. We're sort of stuck, right? We need a landing pad to land all this heavy equipment to make the landing pad. So, well, how do you land it the first time? How do you land the first few times until you can build out this infrastructure? So we're sort of stuck in what we run into in space resources, a lot of a chicken and egg problem where we sort of are in a situation where it's hard to get started. Well, and that's where our team, sort of the team in Mojave, the smaller research team that's been working a lot of this plume surface interaction stuff, started thinking about how do we solve this problem in the way that makes sense to us from the applied propulsion group. And we started sort of thinking about how do construction projects, what do you do if you're going to build something on Earth, right? You don't go out to a construction site and the step one is not drag the power lines with you to get started. You bring a portable generator. And you turn that generator on, you start construction, and at some point you are going to connect into the grid and you can turn off your generator. But that doesn't mean like, okay, well, obviously the generator is obsolete and we really should have concentrated on the power lines all the time. It's a tiered approach. You need one to get to the other. And that generator trades fuel consumption for its deployability. And to us working in the propulsion world, it was like, well, that's pretty similar to how rockets work, right? We consume propellant and we get reaction force out of it. We get reaction force that doesn't care where it is. It doesn't care if it's in atmosphere. It doesn't care if it's in vacuum. It doesn't care if it's in gravity. Like rockets will always push. Now there are better and other ways to push depending on your environment, but rockets at least will always work. And so that's kind of where we're looking at it is how can we use technology analogous to rockets, let's say, propellant consuming technologies to kind of push our way past this chicken and the egg problem. And how do we, as we started looking at it, it's like, as we look at a lot of the challenges on the lunar and Martian surface and in space generally, this perspective of starting with a non-sustainable solution to get to a sustainable solution applies in a lot of different places and a lot of different problems. So what really are these problems? I'm calling them nails in search of a hammer, right? We've got our rocket-based technology. Let's start looking for problems to hit it with. So the first one, and I separate landing pads out into two categories, are initial deployment and landing and repeated landing, right? So when you first get to the lunar surface, how do you get your first infrastructure down? And then how do you start landing enough stuff to have a lot of infrastructure? Then how do you do surface construction? How do you survive the night, right? We want these missions to be longer than a couple days. And then how do you start prospecting for the resources that you really need to start doing excavation and doing valuable work on the lunar surface? So let's talk about what are those space resource technologies and how does propulsion play into each of those. So we'll start with initial deployment and landing. So the current state of the art for landing is just send it. We'll land on this loose, unconsolidated surface. And I'm showing this picture in the upper right again. The Apollo missions got lucky, right? They were near the limit for mass of a vehicle before you start getting deep cratering. Surveyor was not so lucky, as other pieces of surface infrastructure nearby to these landers might not be. got absolutely destroyed by these ejecta plumes. And we're at a very, very exciting time right now where I don't have to just talk about pictures from the 70s. We have some brand new data that we're able to pull in here and show off. Where I've got some images from the Blue Ghost landing here, and let's see, it kind of goes from upper left to upper right to bottom right, and we kind of curl around here. I include the upper left image to show how clear things are before these PSI effects start taking over. And then as we start getting closer, we can see the lander getting closer to the surface. We can see sort of shadows from the exhaust plumes from the rockets, and it starts to get very, very dusty with this light dust. And then in the bottom center there, you can see that's not the exhaust plume from the rocket. That is dust and dirt kicking back up because they have sort of this ring of the Pulsar CS thrusters um, that they're landing with, and that impinges a big plume of dust and dirt really underneath the vehicle, and eventually once it touches down, you can see this big chunk of ejecta flying out. So we have a lot of validation that this is indeed a thing that we need to be worried about. We should be getting a lot more really interesting data from the Scalps payload. I think they're still processing that right now. I'm looking forward to hearing sort of how what more quantitative data we get out of that payload here fairly shortly. But needless to say, even from the initially released video, we can see that this is certainly a problem, and it's something all of us landing on the surface should be taking seriously. So if this is the state of the art, where do we go from there? Well, that's where we introduce, I think, one of the most exciting technologies we've worked on originally at Maston, now at Astrobotic, called FAST, which you may have heard of. This got a lot of media attention when it came out, but it's our in-flight alumina spray technique, where we're actually we propose bringing with a bunch of alumina material and injecting it into the rocket engine so it melts, sprays out of the rocket, and then refreezes back on the surface to create a landing pad as you're landing. Kind of based on an HVOF gun, which is actually a machining implement that you use to recoat and rebuild up material on like a lathe if you're trying to repair something. But it allows us to kind of leapfrog that chicken and the egg problem where we can land a lander that creates its own pad, and that first lander can be carrying the materials and the infrastructure necessary to build out more landing pads for other landers to come after it. So it's a really good sort of vanguard to go forward and set things up. It was funded under NIAC, the original development, where we did a lot of the computational work on this. Didn't get a phase two because they said it was too well developed, but that, yeah, perhaps they're just being nice. But the other issue with it is if you view it purely from a mass perspective, right? If you look at it with the optimization that we use today for judging lunar missions, the mass trade is not good. You do have to you're carrying your whole pad with you, right? You have to carry enough material to create a landing pad, and it's all on board with you. The overhead for the injection system is not that high, but the overall mass of the that you have to carry is not great. But if you're looking at a different optimization, if you're saying, I want to be able to land successfully and not create a giant hole and have the landing pad work well, then, it trades much more interestingly. So that's where we're looking at applying this propulsion technology to get us in a position that we can really use space resources. So what then happens after we get the first stuff down? Maybe we use these fast pads, or maybe we just accept that we're going to throw some dust everywhere with the first couple landings. Where do we go from there? So the obvious long-term solution that's better in a certain way than these fast pads is to use lunar regolith as our feedstock, right? There's the Ethos paver again. We've got a couple images from Icon, both for lunar landing pads and for just bulk infrastructure development. We want to use fully ISRU solutions, right? We don't have to bring any of the feedstock material with us if we do that. But all of this requires a lot of energy, and mobility, which is very time consuming. And you can spend all this time setting up as much energy as you need to run these things. I know everyone's trying to bring the energy down, but we're still talking in the many kilowatts and up to be able to do these laser and microwave sintering, all this melting, casting processes that we're doing with all this stuff. So it's obviously the long-term solution, even for like bulk regolith, moving it, having big bulldozers move things around. That's clearly the end state solution that we want to get to, but how do we start? And our solution at Astrobotic has been to do something we're calling ReNest, which is refurbishment enhanced non-sintered extrudable surface technology. So that really what it is it's a ceramic binder agent landing pad, right? So there's a lot of people working on binder agent construction. Some are polymers, some are thermoset versus thermoplastic polymers. There's other sort of glues and things. What we're using is a ceramic binder agent, where we're bringing that from Earth. The idea is, and we're mixing it with regolith, and that forms our material. And why that's particularly interesting for us is this material is unlike the other binder agent technologies, is resilient to rocket engines, right? It can get really hot because it's sort of based on a ceramic technology. So we worked on this. This was a technology originated out of Pisces at the University of Hawaii Hilo, and we're going to be testing it at Michigan Tech, paid for by NASA. But we approached it with what I'd call we approach it from the right rather than from the left in how we're from a timeline perspective how we're looking at this. Rather than creating this material and well characterizing it and then eventually getting to testing, we started out by saying, hey, let's mix this thing up. We don't totally understand everything about it, but before we get too far down that road, let's just see if it works. So let's shoot a rocket at it. And so that's what we did. We've got that paver there. We're shooting our rocket directly at it, and it put up with it really well. Um, and what we also did is because it's this slurry mixture that cures, and I should say I didn't get to it on the last slide. Um, because it's the ceramic binder agent, the evaporation of water out of it is what, and the water can be reclaimed. It's not used like it is with a terrestrial cement or concrete. So the water is recyclable in that sense. Um, it doesn't require energy input to cure, so it's very low energy. It's non-sintered. It allows you to create this without a significant heat input, so it has very low energy requirements. You just have to bring the binder with you. And as we saw here, it puts up with a rocket engine. We also did a bunch of these test fires where because it's a slurry, we cut some of these pavers in half and glued them back together with that slurry and fired right on the joint. Those also survived. And we also did some refurbishment of we want to be able to land on this pad multiple times. So obviously we leave an erosion crater where the engine was. So we went in, we ground those back down, and we refilled it in with this slurry again, and we fired on those repaired points. And those had the same performance as the original unfired pavers. So that was pretty exciting that this is something that we can land on, we can repair multiple times. We don't need a bunch of energy infrastructure to do it. And we could conceivably use this for other applications, right? If we extrude it out, we can make all sorts of shapes and panels and beams and things out of it that sort of can tide us over until we can get to that high energy cast, melted, sintered technology that we want to use for surface infrastructure. So the thing that really gave us the idea that we could use this for that is we did some compressive strength and flexure and other stuff analysis of these pavers. We chopped them up and tested them after the fact. And terrestrial concrete is 15 to 30 megapascal compressive strength requirements. We're not there with this. It's a geopolymer concrete is the most analogous solution there. But if you consider these in the context of 1/6 G and the loading that they're going to see, we think it's actually a pretty interesting solution there. So it's sort of, again, saying there's not one solution for how we're going to do things and how we're going to use lunar resources. There's this tiered stepwise approach where we're going to, in the early stages where we don't have energy, where energy is scarce, we're going to have to use mass to make up for that with something like these pavers. And then once we get to a situation where we have a lot of energy, now we can start saving on mass. So we're continuing that development as well, coming up with sort of printers to make different things. We're going to try and deploy this in a thermal dirty vacuum chamber at Michigan Tech. This is sort of similar to a lot of the regolith printing stuff that we've seen out there, but we're sort of, like I said, we're kind of coming back and cleaning up a little bit from initially saying, hey, can we fire a rocket at this, to now, okay, let's actually make this work. It's a technology for lunar surface infrastructure. Speaking of lunar surface infrastructure, we want it to last more than a few days. So we got to survive the night. I imagine a lot of people on this call are very familiar with the challenges of lunar night survival. It gets very, very cold, especially at the equatorial regions. It also gets very cold at the poles, but there's some other solutions you can get around there. So right now, kind of the state of the art, our main solution, our long-term solution at Astrobotic is what we call LunaGrid, where we're using vertical solar arrays to place them in multiple locations around the poles. So some of them are always in sunlight. So we can continue to provide survival and operational power to various payloads, and we're connecting those with, a power grid and really producing that power grid on the moon. But that's really applicable to polar applications. Um, then, nuclear has always been sort of talked about as an option. And, RTGs and RHUs are developed technologies. They are just very expensive, and there's a ton of red tape associated with using them, right? If you say, hey, I want to slap a bunch of plutonium on top of a giant, explosive missile, you're going to have to get a lot of approvals to do that. And then we're also getting to a point that there's not quite as much plutonium-238 around as there used to be, which is a good thing, but it's also problematic for trying to create more of like the MMRTGs and stuff that we've been using on Mars. So there's companies looking at other solutions for that as well. But the end state is really surface fission power, right? When I talk about end state where we have megawatts of power, we can survive the lunar night. The waste heat from surface fission power is really the be all end all. But we need to get to that point first. There's also some crazy other ideas. Crazy is the wrong way to say it. Interesting other ideas that I really like the thermal wadi concept where we heat the ground up and then use that as our heat sink during the night. We could also look at caves and lava tubes and space-based solar. And so Survive the Night has a lot of future solutions, but not a lot of near-term solutions that are easy enough to deal with that don't have the challenges of RHUs and stuff. So something we've been working on for a long time is a Survive the Night solution we call NIGHT, the Nighttime Integrated Thermal and Electrical System. Previously called it MOWS, metal oxidation. And really what you can think of it, how this ties back into that deployable rocket-based technology is it's effectively a really slow hybrid rocket where we're metering an oxidizer over a solid fuel to create heat. And the big advantage there is you can turn it off during the daytime, right? All these other heating solutions, they create heat whether you want them or not, especially the nuclear solutions. So during the daytime, when it's getting hot, you got to reject all that heat, and that's a challenge. With this system, you just turn it off. And it's also immediately deployable. You land, you turn it on, you're good to go. So our system, we were oxidizing metal with hydrogen peroxide and creating hydrogen gas from that, and then looping that hydrogen gas back in and reacting with the peroxide in a fuel cell and sort of having this closed loop where it was very efficient. We got it up to about 10x the specific energy of batteries. So we're trying to land between batteries and nuclear at that point. But we'll get a little bit more into why I think this is very valuable in just a second. The last item I wanted to touch on was our work in prospecting, mining, excavation, that kind of work. So really, the proposed current solution towards excavating and mining is bulldozers on the moon. We need to fly big, heavy things to the lunar surface to be able to dig holes, to excavate a lot of material. But even as you fly those big things up there, there's a ton of serious issues that the lunar environment presents. Reaction force is one of them, right? If you're trying to dig or drill into the surface, you're not pushing very hard into it, and its normal force to you is not that strong. What in mining we called pressure on bit to be able to drill or dig is not there. And I mean, you could try and overcome that by being heavier, which is problematic, or using, let's call it in situ derived mass, which load a bunch of boulders into the back of your excavator to make it heavier. But that has diminishing returns in 1.6G, right? Those boulders themselves aren't that heavy. So you run into to issues. So IPEX overcomes this with their counter-rotating drums. So NASA Kennedy has been working on this for a while. But it's still an issue that we need to figure out. How are we going to do prospecting? How are we going to do drilling? How are we going to do this level of excavation? And it's non-trivial to figure this stuff out, because if we want to have large infrastructure investments in extraction, and I show Interlune's new image they're showing of their helium-3 mining thing here. That's just to show that there's a lot of down mass associated with this. We got to pay a lot to fly a lot of stuff out there. If you look at the analog in the terrestrial mining industry, you have to move from a resource to a reserve before the real investment is going to happen. And the delineation between a resource and a reserve is both scientific and economic, right? We have to know that's there with ground truth. We have to know how much is there with a high level of confidence. But we also have to know that it's economically viable to extract, right? If it costs too much, then it's not really a reserve. And so we've got to move these resources to reserves. And for that, we need to do a bunch of prospecting, right? We need to dig a lot of holes. So this is probably the most exciting thing I think we've worked on from a technology perspective, and that's our rocket mining system, right? We're talking about propulsion applications to space resources. So Rocket M, our rocket mining system, is actually an acronym, a resource ore concentrator using kinetic energy targeted mining. That one took a little while. But this was actually developed for the Break the Ice Challenge a few years ago. And the idea is we use that deep cratering concept from before to say, when you're landing, you don't want to dig a hole. What if you did want to dig a hole? So this was developed with Dr. Metzger at UCF and some other partners as well to kind of come up with this holistic system where we'd fire a rocket in a deep cratering configuration with a dome over it. We'd sort of dig this deep, narrow hole, and all the material, polar volatiles and other resources, would get sort of sucked out of that or blown out of that by the rocket and filtered out by the aquafactorum system that was developed separately than this. But we're able to extract all the polar volatiles as well as all the volatiles from the exhaust. So we're notionally this would be a hydrogen oxygen rocket, so we get the water back. So then you start filling up your water tank. You go back to a processing plant where you're electrolyzing that or something, and then you get your fuel back. You go out and you dig some more holes. So this is sort of a weird way to look at it. It's like, why would you do it that way? And I think there's two really specific reasons. One is that we don't talk about a lot is tool wear, right? In mining equipment, your excavation and mining equipment, the teeth and the drill bits and everything, those have a wear life measured in hours. Like even when they're hardened tool steel. Um, it may last a while, but it's not going to last that long. And so in the mining industry, we go out and we replace components, right? There's a lot of machining and replacement work that happens on mining sites. That's going to be a lot harder on the moon. So by using this technique where we're the mining that the bit effectively is gas, we're able to avoid a lot of those repairs from dealing with the abrasive regolith contact. And the other point that was really interesting that sort of led us to this is part of the development for this was deep cratering, and part of it was some ablator testing we were working on. We were working on ablative coatings for reentry for a different project, and we were firing rockets at them. And we were getting them really hot and they're glowing red, and it's great. And we were doing that testing right around Thanksgiving. And we decided, let's cook a turkey with this. And I've not included the images because they're a little gross. But we decided to put a frozen turkey out there, or a thawed turkey, and fire the rocket at it to cook it. And what we did not get was a burnt turkey. What we got was a bunch of chunks of frozen turkey all over the desert. And that makes sense if you think about it. Rocket plumes are very hot, but a majority of their energy is kinetic. Because if you've done a good job with your rocket, you're converting the heat and pressure inside the chamber into velocity going out the back. That's the whole point of a rocket, is to have exhaust gas velocity. So almost all the energy is kinetic in your plume. So to that point, it's like, well, we could mine ice doing this. We could blast it in, and it's not going to transfer that much heat. We'll get solid ice back out. So that's a bold claim to make. So we decided to test it. So we got a phase one SBIR to test out this bold claim that we could extract solid ice using rocket plumes. So we devised some hardware to test this with that same rocket you've seen a number of times in this presentation. And the visualizations show a taller dome. When you start doing the actual calculations, the dome is much shallower. But we had to find some way that, we weren't going to like vacuum suck all this stuff out and build a whole aquafactorum system. So we created this double dome system where the gases would slow down, and so all of the liberated material would fall out of the gas stream and the gas could escape. And then we also had to create some really janky frozen regolith simulants. Right. So a lot of people have put a lot of time and PhD effort into how do you create icy regolith simulant in a reasonable way. And we had to try and replicate that in the desert with no facilities when it was 90 degrees out. So that was a little tough. So we did a cemented regolith, which was pretty easy, right? We mix in 3% water, we poured on a bunch of liquid nitrogen, we did it in layers, and we created this cemented layer. And then for discrete, it was a little more challenging. We called this the margarita regolith because we poured the regolith and ice into a blender, blended it all up so it was discrete fines, and poured that down and froze it with liquid nitrogen on the test site. And we put some thermocouples in there to see what happened. Uh, and so the result was it worked, right? In both the discrete and cemented regolith, we were able to dig holes and we were actually able to go out to that collection tray and find pieces of water and ice in there, which was very exciting. Unfortunately, it was very hard to find much ice because by the time we fired and then saved the rocket and vented everything, it could get over there and undo all the bolts, and we're out in the 90-degree heat in the sun. A lot of it had melted, but we had individualized chunks where you could see that it wasn't just water that had deposited, it was ice and then it had melted. And we also saw in our thermocouples that we weren't melting the ice, right? The thermocouples, even centimeters away from the edge of that crater, didn't see any meaningful change in temperature. And we extracted, even with our very questionable setup here, um, three times more mass of ice than we used mass of propellant to get there. So we were pretty excited that this extraction method worked. And with the last few minutes here, I'm going to run through how does this all play into this fuel consumption concept into a circular lunar economy. Um, so this is kind of where we come back to that lunar night survival system, right? Where we're using metals and we're reacting with hydrogen peroxide to get heat. And for our application, we were using very lightweight metals to try and reduce the launch mass of the system. But if you could get in situ metals, that would be much more interesting. You wouldn't care about their mass or their energy content because you could just get more. So we're looking at the sort of one of the first applications of ISRU on the lunar surface is going to be O2FR, oxygen from regolith. So there's carbothermal reduction, there's the various forms of electrolysis, but it's going to be something like that. And those create oxygen. And then if you do it right, there's some processing you do to separate the metals. But if you don't, you have a mixture of metals. Well, we can use a mixture of metals. We're just burning it. We don't care. So we can burn that in our heater reactor. And what we can do is if you go to the oxygen extraction people and say, hey, not only is someone buying your oxygen, we'll buy the other side of that and we'll monetize this waste stream. So that makes it much more interesting for the O2FR folks to actually make an economic case for this extraction. And then if you start looping it in, if you're extracting oxygen, you might be extracting lunar water as well. Um, so if you can, that when you're extracting water and you're cracking it into hydrogen, oxygen, the long and short of it is you end up with extra oxygen because you want to run your rocket engines rich, and we can get into the rocket science side of that later. But what do you do with this extra oxygen or the O2FR? How do you store your extra oxygen? Well, if you have water, you can create dilute hydrogen peroxide, which is exactly what we're using in our fuel cell and MAUS reactor. So, okay, now we can buy that. We're buying the metal. We're creating heat and electricity for night survival. And at the end of the day, that metal, all the way through this metal oxidation reaction, we start with metals and peroxide, and the end state is all of those oxygens and hydrogens are bonded to the metal as metal hydroxides. Metal hydroxides are exactly what we need for our geopolymer landing pad material. So now you start with this extraction and you end up with propellant and surface structures. And it's sort of enabled by this internal processing that also has a valuable output of your heater. So this is just one example, but it seems to me that not the rocket-based, consumption-based model of lunar infrastructure and space resources not only allows rapid deployment in a way that gets us past sort of this, chicken and egg problem, but also could exist long term, right? If you want to go build your next moon base, you're not going to just expand one until you get there. You have to go start from scratch again. So you need your portable generator again. You need all these technologies to go do that. And you have them as backup. And then you also have them as an option to sort of close the loop on this economic cycle. So that's kind of where applied propulsion is taking all of these rocket technologies and applying them to lunar surface resources and infrastructure in a way that I think is very valuable and interesting to incorporate into the nascent lunar economy. So with that, I think we have a few minutes left for questions. So hopefully Jared can jump back in here and we'll take some questions.
Hey, great talk, John. Really informative, cool stuff. Thank you. Um, Before we get started, yes, everybody, please punch your questions for John in the Q&A. I'm gonna punch in the chat for you all to see a link to the AIAA Space Resources YouTube channel where this and all of our other talks are uploaded. So you can view them after the fact, share with your friends, enemies, whoever you want. Also, a link to the AIAA Engage page where these slides will be uploaded after a few days. Anyway, now on to the Q&A. Asher Zale says, looking forward to testing with you at Tech. Cool. And
Yeah,
now,
looking forward to that as well. The chambers and testing capabilities that you guys have built up there have been are really enticing. We're looking forward to it. Hopefully during the summer, but we'll see.
Paul says there's 1 week of summer and it was last week. Uh, so you missed it. But anyway, Nirma Cheluk asks, amazing presentation and work done by Astrobotic. I like the point that you made that construction material properties do not need to match terrestrial since we do have a very different set of loading criteria. Designing structures around the availability of types and strengths of material is crucial while also setting the life expectancy of certain structural systems and components. What are your thoughts on the design of shield structures like berms and walls to protect the surrounding infrastructure from rocket plumes?
Well, I really like that question because it plays into some of the earlier work that we need to keep continuing on the computational side of things to understand what is the minimum amount of structure we actually need to build. I think pads are always going to be critical for the mitigation of that crater formation and the mitigation of the high angle, high speed ejecta that could endanger orbital assets. But for the surface assets, yeah, we're always going to be blowing dust, and we really should have berms around all of this. But how big do those berms need to be? How far away do they need to be? How tall do they need to be? What angles can they be at? And this is something we've actually been working with Texas A&M on simulations of, and I was going to include it, and I didn't really have enough time or space. We recently published, or they recently published, Dr. Hassan, Zohaib Hassan at and his postdoc Akib Sawar at Texas A&M on a model that we validated with a lot of our terrestrial testing to look at how fence geometry, mainly looking at height and distance from the plume, how those affect the trajectory angles of the ejecta that's coming out. If you get it too close, does it just blow over the top of it? If you get it too far away, is the ejecta, not affected by it? How do we design those berms and structures such that we're not taking up a ton of space for our landing area, so you don't have to drive like 6 kilometers to get to your landing site, but also that we're not using so much material that it's actually feasible to build them. So there's a recent publication on some of the simulation work that we did there that's been very interesting, and it's something I definitely want to continue refining those models, and refining those models comes back to a lot of the data acquisition work that I was talking about earlier in the program. So my thoughts are I think we need to keep exploring to figure out how we minimize those.
Mm-hmm. Absolutely. Well said, and thank you for your question, Nirma. I don't see any others in the Q&A, so I'm gonna jump in with a question. You mentioned the FAST technology to spray alumina or to bind as you descend. Um, One question I have, I'm a lunar scientist, and I'm always interested in the pristinity of a site. And one thing I'd be worried about is because you're coming down with an if you're coming down with an HLS size vehicle, you may loft some material into orbit, or some may go around the lunar globe and land, and it may be contaminated. So, how can we help mitigate that kind of contamination to keep science and other historic sites on the moon pristine if we were to use that technology?
So I think that technology is going to be really helpful in limiting the contamination, right? Because we're limiting the amount that, one material is being moved from where it was deposited, where it's originally been, to a new location, right? So we don't want some collection of regolith from one area, let's say Mare, going on to the highlands, and when we try and do sampling there, saying where is all this stuff coming from? The other thing is a lot of the exhaust species of rockets are not something that you want to find in your evaluation of the lunar soil, especially if we're using traditional hypergulls like we're using now. And then as we move to cryogenics, we're going to have a lot of water in the exhaust, which could contaminate a lot of things. So something that we concentrated on during the FAST development was it was a lot of thermal work to because when you eject the particles, you want them to get hot enough that they melt, but not so hot that when they hit the ground, they don't re-solidify. And there's a lot of particle impact to unconsolidated material simulation that we had to do to figure out how are we not just making a bunch more impacts with ejecta coming out? How do we get those to come down slow enough and cool enough that they're liquid and then they resolidify. And then once you start having a surface, they're not bouncing off and, like you're saying, going and contaminating other areas, but just resolidifying on that surface. So getting those particles to get the right amount of heat input was a very challenging aspect of that, and it's something we did computationally, but we really need to start evaluating experimentally to make sure that when we're doing that, we get that immediate resolidification, so we're limiting the contamination of the lunar surface.
Great answer. Thank you. Another one in the chat. Nithyanagopal Goswami asks, are the plume geometries the same when you get close to harder materials?
They are not. So one thing that we run into with PSI is that one, we're trying to do it in vacuum. So you get this rarefied flow, right, where it comes out of the nozzle and it disperses and you get, Brownian motion of particles when there's not enough pressure to hold everything. But as you fire for longer and you get closer to the surface, you start to build up a localized atmosphere that starts to consolidate your plume and to bring it back down, kind of similar to how you'd have on Earth. So you start getting more excavation. And then if you're looking at loose versus hard material, that loose material, you're going to be digging out, you're going to have an evolving surface. So the gas pressures and velocities have to deal with that. Versus if you have a hard surface, now you're going to get that gas is coming out supersonic. So you're going to have shock waves when it hits the surface and bounces back. So if you look at a lot of, and this is in publications all over the place, but if you look at the pressure fields and the velocity fields for the plume as it impacts a hard surface, usually simulated as just impermeable, you'll see supersonic reflected shocks come back up and hit the vehicle. And that's actually something really challenging to deal with terrestrial vertical takeoff landing. That's actually what crashed the first Morpheus lander when NASA was developing that technology for landing was supersonic shock waves on vibrating the IMU when it was landing, and causing issues there. So yeah, the plume dynamics not only affect the pressure waves and velocities around there, but that you have to those waves are real and they impart forces on both the vehicle and the landing pad. So you have to account for those in the design of your pad and your vehicle and your descent profile.
Complicated stuff.
Yeah.
Um, Perfect. I don't see any more in the Q&A, and we are almost at time, so I'm going to call it. John, thank you so much for sharing your expertise and the expertise of your team and all you work with.
Yeah, I want to
So
give a big shout out to the team that's worked on applied propulsion is myself, Travis Vizanski, Connor Lukin, and Amir Bayani have been and the main team, but everybody in the Mojave office has done a bunch of really fantastic work, as well as yeah, that whole team has been fantastic. So looking forward to continuing the work.
yeah, well, thank you all for your contributions to this field, and best of luck on all the upcoming missions and projects.
Thank you very much.
And to all the you attendees, thank you all for coming. A lot of you are repeat attendees. I think I see a couple of new people. So thank you for checking out our webinar series, and be sure to stay tuned for June's announcement coming in the next couple of days. So we'll plan to see you next month. And John, thank you again for sharing everything you did.
All right. Thanks a
Have a
bunch.
good day, everybody. Bye.